Okay, so this is more of an optional topic, but still it can be interesting because it will give you a new perspective on vectors and a dot product. So Fourier series is a tool that's used a lot by engineers, especially electrical engineers, to analyze signals or basically decompose a function into smaller pieces that you can understand more easily. So just remember that so far, when we have discussed vectors, there are things that you can do with vectors. So for example, if you have two vectors, then you can add them together, right? And then you get a new vector. And also if you have a vector, you can multiply the vector by a real number and you get a new vector. And finally, the operation we have been discussing so far is that if you have two vectors, then you can multiply them with their dot product and you get a number. So notice that here you start with two things of the same nature, which are two vectors. You end up with a thing of the same nature, another vector. Here you start with a vector and a scalar and you get a vector, but here you started with two vectors and you got something different. You get a number. Okay? And now it's useful, a posteriori it has been proven useful to just abstract a little bit of what we consider a vector. So naively you can just think of a vector, right, as an arrow in space, so something with size and direction. But you may decide to call a vector anything for which you can any object for which you can perform these two operations. So if you have two mathematical objects, a class of mathematical objects, and you can add them together and multiply that object by a real number and get a new object in the sorry, small glitch. I was saying that with vectors you can add vectors together, you get a new vector. You can multiply a vector by a number, you get a new vector. And so you can ask whether there are other objects for which you can do that. So let's look at functions, okay? So when you have functions like f of x equals x or g of x equals x squared, right? You get these two functions. You can think of them as actual mathematical entities, right? So the function itself becomes a single object, not like a collection of points. Think of the function as the entire curve. And so you can add functions together, right, and you get x plus x squared in this case, or you could multiply a function by a number and you get 3x. But so if you think about it, that's precisely the analog of adding two vectors together and getting a new vector, or multiplying a vector by a number and getting a new vector. Okay, so you the only thing you were doing is that just follow this analogy with the first two operations. Then it would not be that interesting because we already knew that we could add functions and multiply them by numbers. The point is that if you believe that in a way they actually should behave like vectors, then you would like to define like a version of dot product. So can you find so a dot product, instead of the usual bullet for a multiplication, I'm using like a square, so in order to distinguish them. But I want to define a dot product between two functions. which should be a number. Because remember, the point of a dot product is that it takes two vectors and gives you a number. So it's not giving you a new vector. So this should be a number. So for example, these the usual multiplication of two functions, right? That's a new function, so not a number, so this does not work. Right? In particular, so what we want to do is how to find a way to extract a single number from a function or from a collection of functions. Usually some ideas that you have for doing this, when I have asked this in the past, is like, well, someone says, maybe you can take the derivative, right? So if you take the derivative, you get, like for example here, 1. So it seems to be a number, but if you take the derivative of something like e to the x, it doesn't matter how many derivatives you take, you never get to a single number, right? So derivatives do not work. You could also try to do things like evaluating the function, say from at some point, like say 0, and you are extracting a number. The thing is, like that number that you're getting from the function is not behaving in the way you would like it to behave in terms of the other properties that dot products have. So you could pause the video if you want to think a little bit more about what could a potential definition be. But like the idea of a Fourier series is like, say, if you restrict your functions to some interval, like from -pi to pi, then the actual definition of a dot product should be the definite integral from of the multiplication of the functions. Okay, and well, I will let you keep watching the rest of the video to see what happens, but you can use this to define a norm of a function. It would be something like this. Maybe more interesting is that, for example, say in the particular case that we have for these two functions, the dot product between x and x cubed, x and x squared would be the integral from -pi to pi of x squared dx. And since this is x cubed, when you integrate it, you get x to the 4 over 4. And you get 0, which means that these would be two vectors whose dot product is 0. And remember that I mentioned that when you have two vectors whose dot product is 0, well, you should think of them in the usual sense, they're perpendicular, right? When you think of them as arrows. But also that means that in a sense, they are independent of each other. So in a way, you should think of these functions as being independent of each other. More generally, actually, you can use this formula for dot product to define a cosine of the angle between two functions. So now this is a weird idea. You should really think about what I'm saying, but I'm telling you that you can actually try to cook up an angle between functions. So again, if you just follow the recipe, remember that the cosine of the angle was the dot product of two vectors divided by the norms of the corresponding vectors. And now this boils down to something like this. Okay? And so the point is, once you know this, you can also try to find functions that behave like I, j, and k. So you could also ask, are there functions which behave like the unit vectors I, j, and k? And the answer is that essentially there are, like for example, yes. So you can check that sines and cosines like sine of x, cosine of 2x, sine of 3x, etc. Like functions which are sines or cosines with different arguments inside the function, like they share many properties of I, j, and k in the sense that they are orthogonal to each other under this definition. So their angle will be 90 degrees, and also that well, up to a constant, they just like you can rescale them so that they become unit vectors. But more importantly, the key feature of I, j, and k was, for example, that you can take any vector and write it in terms of I, j, and k. And what ends up happening in this situation, the analog of this is that you can take any function and write it in terms of sines and cosines. And that's the key idea behind a Fourier series, and that's what I will show you in the application, in the animation. The only caveat is that here you just had a finite sum, and for the case of Fourier series you have like an infinite sum. So the following animation illustrates the basic principle behind a Fourier series. So what I have is the function x from negative pi to pi, as you can see here. So let's just focus on this part of the function, which looks like an ordinary straight line at a 45-degree angle. And what I said is that you can imagine of approximating. So you think of this function as a vector, and so the vector itself can be decomposed in terms of other functions in the same way in which an ordinary vector can be decomposed in terms of the vectors I, j, and k. So the analogs of the vectors I, j, and k, as I mentioned, are sines and cosines. So in the first approximation for the Fourier series, you just get a particular combination of some cosine with some sine. But then the point is that as you increase the approximation, right? So now you added two new terms, which again depends on some combinations of sines and cosines. As you can see, as you increase more and more, add more and more terms, and like I'm already unable to show you how big it's getting, right? Like you're adding a bunch of sums. As you keep adding more and more contributions, the approximation gets better and better. So that means that like you can cook up interesting combinations of sines and cosines to get as close as you want to any desired function. Okay. Now the idea is that this is not a perfect approximation, in the sense that you need infinitely many sines and cosines in general to get the full description of the function. But so this sometimes is used for signal analysis, because sometimes imagine that you want to compress a file or communicate some message. Well, there's that means that you can think of decomposing that message into its Fourier components, meaning into a bunch of sines and cosines, and then you just keep some of them and throw away the rest, because as you can see here already with a couple of terms, you can get a pretty good approximation to the actual function you care about. So this is a technique that's used a lot in image analysis, because that way you can carry less information.